This is the 35th lecture. Was supposed to be held yesterday, but because of power failure, this is why this correction in the date. And what we are going to do is to complete that example of insertion loss synthesis, and then make a discussion of elements of realizability theory. As I said, this example was the first one in the series of discussions that we are going to have on network synthesis. And the argument, we took a very specific example of synthesis, that is to synthesize an LC two-port which is terminated in equal resistances, let us say R0 and R0, and we took R0 can be normalized to 1 ohm if you so desire. Both terminations are equal, then you have a voltage source VG1, the voltage across this is V2, then you know that S21 parameter, that is the forward transmission scattering parameter, S21 is equal to twice V2 by Vg1 times square root of R1 by R2, but both are equal, and therefore that ratio is 1. Our reference resistances as usual are equal to the terminating resistances. Okay. And the synthesis problem is this: we have to synthesize an LC network. Why LC? Because we want to transfer as much power as possible to the load and absorb nothing in the network. Why do we insert the network? To be able to transfer maximum possible power. That means it is a matching network. Alright, that is one objective. The other objective is, and this is why we have to synthesize, the other objective is we want to transfer power to the load in a frequency sensitive manner. For example, if there is a low frequency signal and we have a high frequency interfering noise with it, for example somebody is speaking and there is a shrieking sound in the adjacent room because of a machine running which is at a higher frequency than that of speech, alright, we want to get rid of this. So, we want to transfer power from the source. This could be a microphone assembly and this could be the amplifier. The amplifier is designed in such a manner so that it rejects that high frequency noise and only transfers power at the low frequency, and therefore there are two objectives. One is that if if it is a single frequency application, then all we want is that the network, the insertion network, the network that is inserted between the source and the load should be such that maximum possible power is transferred at port 1, which means that our aim is to make n such that the input impedance is approximately equal to R0. Agreed? Under that condition, the source gives the maximum available power. And then this network is to be lossless such that the power, none of this power is absorbed by n, but is transferred to R0. In the process, if there is a mismatch, if for example excuse me, if this impedance is not R0, then the reflection coefficient will not be 0. Okay? What we want is that the input impedance here should be R0 so that no power is reflected back. But if it is not R0, then a little power will be reflected back. Similarly, if the impedance looking back into the network is not R0, then there will be a reflection coefficient here. Okay? So, the total, not all the power shall be absorbed here, a part of it shall go back. Alright. So, our aim in putting a network, in inserting a network between a source and a load are twofold. One is that maximum possible power should be transferred to the load, and second is this transfer should occur in the desired frequency sensitive manner. It could be a low pass, it could be high pass, it could be band pass, it could be band reject. Okay? This network LC could be any of these types.
Even if we do not insert the network and we terminate it by R0,
right?
So the power transferred will be maximum.
But it will not be frequency sensitive. Okay? So, in this particular situation it is a frequency sensitive. I was waiting for this statement. You see, if both the terminations are unknown, then we don't, and our aim is simply to transfer maximum power, then we don't have to put any network, all right. But this is a specific case, as I said, and it is a special case of the procedure of Darlington, of the problem that Darlington solved, and therefore this problem is known as Darlington's insertion loss problem. Darlington's insertion loss. I have also told you what is insertion loss. Insertion loss alpha is defined as 20, not 20, 10 log 10 of P20 over P2. Is it this way or the other way around? This way, okay. Now, this is therefore the problem. So, what is given is either this voltage ratio V2 by Vg1 or S21 j omega magnitude squared, or alternatively the IPR, the insertion power ratio. If any of these three is given, we can find out S21 j omega magnitude squared. If this is given, then from this we can find out, because n is lossless, we can find out S11 j omega magnitude squared as equal to 1 minus S21 j omega magnitude squared. Okay? If we subtract this from 1, then we get S11. You see, this step, this particular step is a very, very elegant, very beautiful step. What it does is the transfer function synthesis problem. You see, given S21 j omega magnitude squared is a S21 j omega, after all, is a transfer function, right? It relates the the voltage at one port to the voltage at some other port. So, the transfer function synthesis problem, which concerns at least two ports, is converted into a driving point function synthesis problem. Isn't that right? S11 is the reflection coefficient at port number 1. It relates to the incident and reflected waves at port number 1. All right. So, the transfer function synthesis problem is converted to a driving point function synthesis problem, and this is the general philosophy that you will see in all synthesis problems, that we want to convert a complex problem into a simple one. A driving point synthesis problem is much simpler to solve than a transfer function. So, in all synthesis situations, our aim, our primary aim is to convert this problem into simpler one, that of driving point function, and then solve it. Okay. The next thing that we did was, after we find out S11 j omega magnitude squared, we write this as S11 j omega multiplied by S11 star j omega, and S11 j omega, you know, if this is a real function, then its complex conjugate is simply by making minus j omega, all right. And then we said, we used the word a big leap forward. Okay. Suppose a function f of s is given. If a function f of s is given, how do I find out the corresponding function on the j omega axis? That is for sinusoidal excitation. All I do is I put s equal to j omega. That is, I have a general field, and the function is defined at all points in the field. I want to find out the function at a specific location. I simply put s equal to the general variable equal to that specific location. For example, if f of x is given, I want to find out f of 1, I simply put x equal to 1, correct? But suppose f of 1 is given, that is at a specific location, and then you have to find out f of x. In general, this is an impossible task. Isn't that right? Unless you know more about the functional property of f of x. Even if the function is given on a particular line, let us say x equal to 2 or if it is a function of two variables, it is given on, let us say, y equal to 0 or x equal to 0. To go to the general variable f x y from a specific location is an impossible task. Usually it is an impossible task. That is, what you are asking is to construct the whole from a part of it. If I give you a piece of brick, a broken piece of brick, and I ask you to construct what it was originally, you can only guess that perhaps it was a what is it called, cuboid, perhaps, but there is no guarantee. I might have on the cuboid a hemisphere. Okay. So, one usually cannot do it, but in the case of a complex variable where the function is analytic, and by analytic function we mean the function is differentiable everywhere except at a finite number of singularities. If that is so, it turns out that if the function is given on the j omega axis, you see, after all, capital F of S is a function of two variables. One is sigma, the real part, and the other is omega, the imaginary part. It is a function of two variables. What we are given is the value of the function at sigma equal to 0. Sigma equal to 0 defines the j omega axis. Now, the problem now is to go from f of j omega to f of s. As I said, in general this is impossible task, but fortunately the networks that we deal with in practice, or maybe we have chosen only those networks. There are networks which do not behave so nicely. We are not concerned with them. We don't use them because we don't know how to use them. Here, fortunately, what happens is that we can go from the j omega axis to the complete S plane wherever you want by simply substituting S for j omega. So, that is what we do. Capital S11 of j omega is an analytic function S11 of S, and therefore, from S11 j omega, S11 minus j omega, we go to, we substitute j omega equal to S, and we get S11 of S, S11 of minus S. Okay. And the next task then is to choose an S11 of S. It is given as a product. Suppose S11S has a factor S plus 1 in the denominator, then it must also have a factor. You see, it is a product of S11S, S11 minus S. So, if this quantity has a factor like this, then minus S plus 1 should also be a factor. Similarly, in the numerator, suppose you have a factor of S minus 2, then you must have a factor of minus S minus 2 also. So, if S11 of S and S11 of minus S can be factorized into its roots of the numerator and roots of the denominator. Okay. As far as the denominator is concerned, the choice has to be unique. Why? Because we go back to the definition of the reflection coefficient. It is the input impedance minus R0 divided by input impedance plus R0. Okay. And the poles of S11, which are the zeros of Z1 plus R0, Z1 plus R0 is an impedance function. An impedance function cannot have zeros in the right half plane, and therefore all zeros of Z1 plus R0 shall be in the left half plane, which means that in S11S, S11 minus S in the denominator, after you factorize out, you have to choose only those factors which contribute to zeros in the left half plane. The zeros in the right half plane shall go to S11 of minus S. Here, for example, S11S is absolutely clear. Okay. Here, for example, S11S, you will have to choose only this factor in the denominator, S plus 1. As far as the numerator is concerned, you have a choice. Numerator is a difference between two impedances, and a difference between two impedances can have poles anywhere, can have zeros anywhere in the S plane. It is not restricted. Okay. Z1 equal to R0, this defines the zeros, and so you have a choice. You could either choose S minus 2 or you could choose minus S minus 2. Alright, let us say S minus 2. Then this is your reflection coefficient S11, and from the reflection coefficient then you can find out Z1, and Z1 the input impedance from S11S, S11 minus S, you choose S11S, then you find out Z1 as equal to R0 by compendendo and dividendo 1 plus S11S, 1 minus S11S. Alright, and finally you synthesize Z1. Okay. finally you synthesize Z1. We have not yet dealt with the problem of synthesis of a Z1 of a driving point impedance, but in the Darlington problem, in very simple cases, not very complicated, in very simple cases it turns out that the synthesis problem is also very simple, and this is what we wish to illustrate with the help of an example. Yes.
Example you have taken just now, factor s plus 2 minus s minus 2 upon s minus 1 minus s minus 1.
Correct.
There will be two solutions corresponding to this.
There will be two solutions, yes. I am glad you asked that question. To a synthesis problem, if there exists one solution, there exists an indefinite number of solutions, and this is a demonstration of that, there are at least two solutions that you can easily find out. Okay. The problem, the example that we were discussing is S21 j omega magnitude squared is equal to 1 by 1 plus omega to the 6, and I told you this is a low pass filter. It is obvious that the transmission is unity at 1 at omega equal to 0 and it falls off at high frequencies. It is a low pass filter. It is a third order filter because it is magnitude squared, and therefore the magnitude would be of order 3, third order, and this specific case is known by the name of a gentleman, an English gentleman by the name S. Butterworth. So it is called a Butterworth third order low pass filter. These are names, you may forget them, you may remember them. For the present it is not important, but I just thought I would mention the name in with due regards to Butterworth. Okay. The next thing that we do is we find out S11 j omega magnitude squared by subtracting this from 1, and therefore we get omega to the 6 divided by 1 plus omega to the 6, and then I find out S11 s S11 minus s by substituting omega equal to s by j, and that gave us minus s to the 6 divided by 1 minus s to the 6. Then we factorized the denominator. As far as the numerator is concerned, it is either plus s cubed or minus s cubed. Okay. Accordingly, we shall have two solutions. We will look at that. The denominator, as you saw, was 1 plus s multiplied by 1 plus s squared, which gives you s cubed plus twice s squared plus twice s plus 1, I hope I am right, and minus s cubed plus 2s squared minus 2s plus 1. So, let us find out only S11s. We take this as the denominator. In the numerator now we have a choice. It is either plus s cubed or minus s cubed. We shall take both of them and see what the network is. What should we do?
So we can take s also s squared.
No, we cannot, because one is S11s, the other is S11 minus s. If you take plus s cubed here, you have to be fair to S11 minus s, you must give that minus s cubed. Alright, you cannot take any power of s here. Alright, so let us take S11 of s as equal to plus s cubed divided by s cubed plus 2s squared plus 2s plus 1. Now we have to find out the impedance Z1. Z1, for this we have to fix now R0, the terminating resistances. Let us fix R0 as equal to 1 ohm. Then Z1 is simply 1 plus S11 divided by 1 minus S11, and you can easily see that this would be 2s cubed plus 2s squared plus 2s plus 1, and the denominator it would be 2s squared plus 2s plus 1. Agree? Okay. Now the problem is now to synthesize Z1 in a constrained manner. What is the constraint? That the last resistance must come out as 1 ohm, and this is the beauty of Darlington synthesis, that he saw into it. He saw into the depths of this problem and ensured that if you go this way, the terminating resistance is bound to come. As you will see, it is no magic. we shall be able to find the logic at a later date, but it does come. Let us see how to synthesize. 2s cubed plus 2s squared plus 2s plus 1 divided by 2s squared plus 2s plus 1. You notice that this impedance has a pole at s equal to infinity, isn't that right? As s goes to infinity, the highest power term 2s cubed, the highest power term is 2s squared, so it behaves like s. Z1 tends to s as s tends to infinity, which means that Z1 has a pole at infinity. And what we do is we remove this pole. What does that mean? It means that we divide the numerator by the denominator and find out the remainder. That means we shall have s, the quotient will be s, and what will be the remainder? S plus 1. All right. So the next thing that we do is, please follow this carefully, because this is going to be a very important tool in your hand as far as synthesis is concerned. Now you see that the remainder function, after you remove s, the pole at infinity, the remainder function cannot have a pole at infinity. It has a 0 at infinity, isn't that right? As s tends to infinity, it is a 0, which means that the admittance shall have a pole at infinity. Is that clear? If the impedance, this is a impedance equal to impedance plus impedance. The impedance has a 0 at infinity, and therefore the admittance shall have a pole at infinity. So we write this as an admittance, 2s plus 1 divided by s plus 1. Is that okay? I write this as reciprocal of, impedance is reciprocal of an admittance, and the admittance now has a pole at infinity, which we now remove again by a division. So I write Z1 equal to s plus 1 over, what would be the quotient? Twice s plus 1 by s plus 1. Okay. Now you recall that this is an impedance. What is this? Admittance. Then what is this? This is an impedance, right? Admittance plus admittance, 1 by admittance is an impedance, and the network, the synthesis is now complete. You see, you are synthesizing Z1, that is the input impedance. You had a 1 ohm, you had a VG1, and then Z1 is this impedance. Z1 starts with an S, which is the impedance of an inductor of value 1 Henry, then plus 1 by admittance, and therefore you shall have a shunt element, a capacitor of value 2 farads. 2 farads. This admittance in parallel with another admittance whose impedance is S plus 1. That means we have another inductor of value 1, and the last element is the terminating element of 1 ohm, and the synthesis is complete. Okay. The mechanization of this, as is obvious from this expression, is to expand the given function in continued fraction. This is a continued fraction, a plus 1 by b plus 1 by c plus and so on and so forth. It is a continued fraction. So the mechanization is that of continued fraction, and we shall do this again with continued fraction rather than arguing from removal of poles. Removal of poles was done to explain to you the actual mechanism of network synthesis. We were removing poles one by one, poles at infinity. Okay. The mechanization is this: we have 2s cubed plus 2s squared plus 2s plus 1 divided by 2s squared plus 2s plus 1. The mechanization of this synthesis is development of a continued fraction. Continued fraction, that is, you write this here and then you see the quotient is S. So 2s cubed plus 2s squared plus S. The remainder I do not want to write here because then I will go like this. So I will bring it here. Remainder is S plus 1, and in the process you must not forget that this quotient is an impedance, alright. Then this divides 2s squared plus 2s plus 1. You understand the mechanization of continued fraction development? Okay. This you bring here, then the quotient is 2s, and immediately you identify that this is an admittance because you have taken the reciprocal of an impedance. Okay. So you get 2s squared plus 2s and you are left with 1, then you bring this divisor here and your quotient is S, remainder is 1, and you immediately identify this as an impedance, then you divide 1 by 1, 1, 1, 0, and the continued fraction expansion is over. The last element is what? No, admittance. This is an admittance because you have taken the reciprocal. It just happens that 1 by 1 is 1, and 1 more admittance is the same as 1 ohm resistance. It may not be so. If the terminating resistance was 2 ohms, then the result here would have been half, not 2. Okay. So you must keep track of the dimensions, and the dimensions, as you see, they alternate. Starting with impedance. Why is this starting impedance? Because the expression is that of impedance. Starting with impedance, impedance, admittance, impedance, admittance. Alright, and the synthesis is complete. Now let us see any question at this point. Let us see what happens if we take, instead of the plus sign, the minus sign in the numerator. If we take S11s as equal to minus s cubed divided by s cubed plus 2s squared plus 2s plus 1, then your impedance Z1 shall be equal to 1 plus this, 1 plus S11 divided by 1 minus S11. So it would be equal to, yes, 2s squared plus 2s plus 1 divided by 2s cubed, this plus this minus this. So it would be 2s cubed plus 2s squared plus 2s plus 1. Don't you see that this function is exactly the reciprocal of the previous function? Isn't that right? It's exactly the reciprocal. So if you want to argue in terms of poles, first you take the admittance, that is 1 by 2s cubed plus 2s squared plus 2s plus 1 divided by 2s squared plus 2s plus 1, and the continued fraction expansion that we had done earlier shall be valid now also, provided you consider this as an admittance. Agreed? Let us go back to that mechanization. Let me use a different color. If you consider this an admittance, then obviously the first element would be an admittance, second would be an impedance, third would be admittance, and the fourth would be impedance. Is that okay? It is exactly the same continued fraction expansion except that the dimensions change, which means that the network shall now be, instead of starting with a series inductor, I shall have to start with a capacitor of value 1 farad because admittance is S. Then we have an inductor of value 2 Henry, twice S, then again a capacitor of value 1 farad, and finally an impedance of 1 ohm. So this is a perfectly valid alternative network to the first choice that we had made. Okay, we have found out at least 2 networks which synthesize the given S21 j omega magnitude squared. I must tell you, you may not be that lucky You may not be that lucky in the general case, but how to get over it we shall discuss later. I want you to notice two important facts. Can you see both of them? Can you see on the monitor both of these networks? Okay. You see both of these networks share something in common. What is it? That the inductors are series elements and capacitors are shunt elements. Isn't that right? And I said the given function was a low pass function. It is indeed low pass. You see at DC this is short, this is open, this is short. So whatever is fed here goes to the load. Similarly here, okay, at DC this is short, these two are open, so they go. And as frequency increases, the inductor impedance increases, the capacitor impedance decreases, and therefore the transfer function or the transmission goes down as frequency increases. And such such architectures should be obvious from the given specification. Such architecture should be obvious from the given specification. Okay. Here for example it was a third order network, third order function. Third order function, to synthesize a third order function you require 3 energy storage elements. Each of them has 3. Now 3 energy storage elements, now I am appealing to your common sense. They cannot be of the same kind, they cannot be all inductors. Okay. If they are all inductors then it is a trivial network and it cannot act as low pass. Therefore you must have at least one capacitor or at least one inductor. You see one capacitor case is this and one inductor case is this. Now before I leave this problem I want to extend this common sense a little bit further. Suppose to start with your function was, let us say, omega to the 6 divided by 1 plus omega to the 6. Suppose S21 j omega squared was equal to this. Without any calculation, can you tell me what the architecture should be? Okay, between what the architecture of the insertion network should be. Capacitors in series and inductor in shunt. At least 3 energy storage elements. So 2 capacitors, 1 inductor, or 2 inductors, 1 capacitor. And obviously this is one of the architectures. The other architecture would be, other one would be, yes, other one would be an inductor here, an inductor here, and a capacitor here. Okay, these are the 2 possible architectures.
Can you explain this again how you do it just by inspection?
Just by inspection, because this is high pass.
Yes, sir.
It is a high pass network, and high pass network means that capacitors should come in series and inductors should come in parallel. Why? Because as S increases, the inductive impedance increases, so more and more high frequency is favored to be passed from the source to the load. Agreed? Suppose you have to find out all that. You have to be able to find out the values, you have to find those out. You have to go to S11, find out Z1 and synthesize it. Okay? But what I was saying is the architecture should be obvious from the given specification. Let me ask you a trivial question now.
Sir, can we assure that there would be only 3 elements?
Oh yes, that we can be sure because there are only 3 poles. Because the order of the function here is 6, it is a magnitude squared. So the magnitude of the would be of the order 3 and therefore the function would be of the order 3. Okay? Now a trivial question. Could we have, instead of omega to the 6, could we have omega to the 3 here?
No.
Why not? Pardon me?
We can't have 1.5 order.
Say it again.
We can't have 1.5 order.
1.5 order. No, order is not determined by the numerator. Order is determined by the number of poles, the denominator. could we have here instead of 6, could we have 3? Tell me why. No, I know.
It won't be real, sir, when we convert it to.
Oh no, I told you this is a trivial question. The answer should be obvious. And the thing is obvious when you see it. Look at the left hand side. A magnitude squared. How can it be odd? Okay, so omega to the 3 is not permitted. Is omega to the 4 permitted? Yes? Yes. Okay. Now what is this function? Is it low pass? At omega equal to 0 the transmission is 0. It is a band pass function. What does that mean? Can you tell me the architecture now? If it is omega to the 4 divided by 1 plus omega to the 6, it would be an LC series. Okay. In series or in shunt?
Can we both have different things?
Okay. Tell me one possible. Either I shall have this, there must be 3 elements, so I must have, what shall I have here? A capacitor or an inductor. Okay, I leave this with a question mark for you. Why should be 3 elements? Because there are 3 poles. The function is of third order. So there must be 3 elements. But how are they connected? That is a question. I leave it for you to decide. Please do. We conclude our discussion on scattering parameters by taking another example. Another example from the book. This is example 14.5. And the problem is now we make the thing a bit more complicated. We say it's not equal termination. Let's say Rg equal to 2 ohms and RL is equal to 1 ohm. They are not equal terminations. So you will have to take care of different terminations. This is R1 and this is R2. R2 equal to 1 ohm. In between you have, this is Vg1. In between you have a low pass network like this, and the values are 2 Henry, 2 Henry and half farad. The problem is to calculate IVR. This voltage is V2. Problem is to calculate IVR and IPR, and from IPR find out S21 j omega magnitude squared. Okay, this is the question. First, to find out the insertion voltage ratio, second insertion power ratio, and after you have found out insertion power ratio, find S21 j omega squared. You know that they are very intimately related. The product is a function of R1 and R2. Okay. To solve this network, as far as IVR is concerned, IVR is simply found out. Vg1 2 ohms. To find out V20, you simply connect the load here 1. This voltage will be V20, and obviously V20 is equal to Vg1 divided by 3. Agreed? Then you have to find out V2. Okay, for finding V2 you go back to the network. Vg1 2 ohms, 2 henries, half farad, 2 Henry, 1 ohm, and this is V2. You have to make an analysis of this network to find out V2, and the way I do, I find it convenient, is to apply Thevenin's theorem, that is to the left of these lines. Then you see the Thevenin equivalent generator would be Vg1 multiplied by this impedance, that is 2 by S alright. Impedance of half farad is 1 by half S, which is 2 by S, divided by the sum of these 3 impedances. So, 2 plus 2S plus 2 by S. This is the Thevenin generator, and then you have a Thevenin impedance. Thevenin impedance would be the parallel combination of this and this. Okay, we will calculate this in a minute. Let us call it ZT. Then you have a 2 ohm, 2 Henry and 1 ohm. Okay, this is the Thevenin equivalent. Now, it is a matter of calculation now that the source is Vg1 2 by S divided by 2 plus 2S plus 2 by S, from which this factor 2 cancels out, and we are left to it. Then you multiply by S, so you are left with 1 by S squared plus S plus 1. Agreed? As simple as that. And the Thevenin impedance ZT is half farad, that is 2 by S in parallel with 2 plus 2S. So, 2 plus 2S divided by 2 plus 2S plus 2 by S, and once again you can forget about this 2. So, you will get 2 1 plus S divided by S squared plus S plus 1. Alright. So, our equivalent circuit, yes.
So, you have to add this inductor to S.
Where?
This is the parallel combination of all these
half farad, and
we have to add 2S.
I had 2 plus 2S.
No, so that's the parallel combination of the
Oh.
inductor. There's a inductor after that also.
I have done that in the denominator.
No, sir. This is the inductor and capacitor.
This is the Thevenin.
Thevenin equivalent. This is the Thevenin equivalent. Okay. Therefore, my V2 shall be equal to Vg1. I thought you were saying this. There should be Vg1 here. Vg1 divided by S squared plus S plus 1 divided by, no, this multiplied by 1 ohm. The voltage V2 is across 1 ohm, divided by the current in this circuit, that is 2 1 plus S divided by S squared plus S plus 1 plus 2S plus 1. So, I know V2, I know V2 0, and I simply divide one by the other. I shall leave that algebra to you, and my IVR, my calculation shows that it is 2S cubed plus 3S squared plus 5S plus 3 divided by 3. This is the insertion voltage ratio. And now the next question is how to find out IPR. IPR, as you know, is R2 divided by R1 plus R2 whole squared. This we had derived yesterday, multiplied by Vg1 by V2 magnitude squared. Now V2 by Vg1 we have already found out, and I know R2, I know R1, and therefore this is simply R2 is 1 by 3 whole squared multiplied by magnitude of 2S cubed plus 3S squared plus 5S plus 3 under the condition S equal to j omega magnitude square, Vg1 by V2 magnitude squared. Okay. Is that all right? We leave this simplification. The S21 j omega squared, how do I find that? You know that this multiplied by IPR, we have derived this as 4 R1 R2 divided by R1 plus R2 whole squared, and this in this case would be 8 by 9. Is that right? 8 by 9. So, you can find out S21 j omega squared. Alright. the few minutes that are left, is there any question? We are not going to come back to scattering parameters again.
So why we have divided the term mod term by 3?
Mod term by 3 because it is Vg1 by V2. This is not insertion voltage ratio. This is simply the reciprocal of V2 by Vg1. It has nothing to do with the insertion voltage ratio. IPR is not in terms of IVR. Okay, that is the reason. Any other question? Okay, as an introduction to synthesis, this was a glimpse into synthesis of the most usual situation. Most usual situation is I have a source and I have a load. For example, the source is a microphone, the load is a loudspeaker. I have to design an insertion network. I cannot connect the microphone to the loudspeaker. Why not? Why not? Impedance matching. Nothing will come in the loudspeaker, alright? Because the microphone is a high impedance source and the loudspeaker is a low impedance load. Typically 4 ohms or 8 ohms speaker, alright? So I have to design an insertion network such that maximum power from the source is transferred to the load. Alright. In between, of course, I have an amplifier. In the usual situation, I have an amplifier which boosts up the power. But in a passive case, for example, in a passive case, I can design an insertion network such that maximum power is transferred to the load. This was, as I said, the usual situation. Now we shall try to approach the problem of synthesis in a systematic manner. And one of the problems is, given a transfer function or a driving point function, given a function in the S domain which can be either dp or transfer, either dpf driving point function or transfer function, the task is to find a network. Well, H of S obviously is the Laplace transform of the response to Laplace transform of the excitation with initial condition equal to 0. This is the definition of a transfer function or a function characterizing the network or any system for that matter. Now the problem is to find a network, at least one network, and you know if one network exists, there exists an infinite number of networks. To find at least one network which realizes this. The first question that one asks is this realizable? Is this a realizable function? For example, suppose I am asked to design a network which realizes the simplest synthesis problem, which realizes Z of S equal to S. Obviously it is realizable. Why? Why? No question of poles. S is the impedance of a 1 Henry inductor. I don't care about theory. It's realizable. Okay. If it is 1 by S, yes. Even then it's realizable. Alright. 1 by S is a 1 farad capacitor. But suppose it is a transfer function. Suppose it is V2 by V1 equal to H of S equal to S. Is this realizable? Why not? It is an unstable function. Okay. So one of the criteria for realizability is that the given function must be stable. It has a pole at infinity. Pole at infinity of an impedance function or admittance function is perfectly alright because we know how to realize it. But pole at infinity of a transfer function makes the transfer function unstable. That means as frequency increases, the output increases indefinitely. Alright. So the output is not bounded even if the input is bounded, which means that the function is unstable. So one of the criterion for a transfer function synthesis is that it must be stable. And the other criterion is, there are two criterion. Other criterion is that if you want a real time realization, that is if you want to find out a network which works in the laboratory to a given excitation, it gives a given response, obviously the network must be causal. It should not be anticipatory. Now what is the stable and causal? What is the criterion for causality? How do you define causality, or how do you characterize a network to find out whether it's causal or non-causal? We excite with a unit impulse function. That is, we excite. I am sure you know this. This was done in signals and systems. You see, the point is, okay, forget what was done in signals and systems. The point is, the output should not precede the input. Output should not anticipate the input. Okay, and this easiest way to do this is to apply unit impulse. The output should appear only after the impulse is applied. That means, what is the response? Ht, the unit impulse response, it should be equal to 0 for t less than 0. This is the criterion for causality. For a linear time invariant system, the causality is guaranteed if Ht equal to 0 for t less than 0. Alright. For example, if Ht is e to the minus at ut, if the unit impulse response is this, it is a causal function. Is that clear? On the other hand, if Ht is equal to e to the minus a, let us say mod t, then it is not causal, because Ht exists for t less than 0. Before a unit impulse is applied, there is an output. Therefore, it is not stable. Now, it is not causal. This is in the time domain. What about the frequency domain? How do you find out, given an h of s, how do you find out whether it is causal or non-causal? That criterion is somewhat difficult and is outside the scope of the class, and perhaps outside the scope of the total B Tech curriculum of electrical engineering. Perhaps it will never be done, but I will mention a criterion which you must remember throughout your life, and it's by a gentleman by the name Paley, P-A-L, no, I beg your pardon, P-A-L-E-Y, Paley-Wiener criterion. Have you heard the name? Where? Which course?
So, Fourier transform, so they give.
Oh, Fourier transform. I am glad. Was it proved?
No, sir, not the result actually.
Okay. The result is, Paley-Wiener criterion says that the integral, if h of s is given in the frequency domain, integral from minus infinity to plus infinity, log of magnitude of h of j omega divided by 1 plus omega squared. Okay, it's hard to see why it is so. It can be proved, but we shall not prove it. The proof is rather involved. The Paley-Wiener criterion says if the network is causal, then this must be finite. This must be less than infinity. Okay, we will go into more details of this next time. Next time would be Tuesday.